Hi students, in today's session we are going to explain or discuss the quantum mechanical tunneling mechanism in STM, or we are going to discuss how the tunneling current arises in the STM, and its explanation is given on the basis of the principles of quantum mechanics. So the tunneling current, that is a current flows between the metallic tip or the end of the probe and the substrate. Current flows between the tip of the probe and the substrate, and the tip and the substrate are not in contact, yet a current is flowing between the substrate and the tip. Now, how is that possible? So classically, electrons cannot move between the tip and the substrate as they are not in contact. So that is, there is a classical forbidden region there. But according to the quantum mechanical tunneling theory, when any particle is incident on a vacuum barrier with a potential energy larger than the kinetic energy of the electrons, that is, the potential barrier in this vacuum region is greater than the kinetic energy of the electrons, there is still a very small yet non-zero probability for the particle to move through the forbidden region and reach the other side. That is the quantum mechanical tunneling theory, which you have already learned. That is, when a barrier exists between two regions, a potential barrier exists between two regions such that the height of this potential barrier is larger than the kinetic energy of the electrons existing here, then quantum mechanically, or as per quantum mechanics, there is a finite, very small but finite probability for the electrons to tunnel from the first region to the second region. So that is what is taking place here. So as all the particles have wave-like properties, that is, the electrons here are also represented in the form of leak-out wave functions. The electrons which are tunneling are represented by leak-out wave functions. Then we are going to explain a feature of this wave function, that is, the electron wave functions have a characteristic exponential inverse decay length k, that is, the wave function psi of this leak out electron or the tunneling electron, which is called the leak out wave function, has a term k in it, which is the inverse decay length, represented by k equal to root of 2m phi by h cross, where m is the mass of the electron, phi is the tunneling barrier height, that is the potential energy encountered by the electron which it has to cross. Okay, so phi is the local tunneling barrier height, or it's also the average work function of the tip and the sample, that is the energy which must be needed to cross over from the tip to the sample. So it is the potential energy or the potential barrier which is encountered by the electron. Okay, so the wave function of the electron is characterized by such a decay length, inverse decay length k, given by root of 2m phi by h cross. So you get it from the equation for momentum. P is equal to h cross k is equal to root of 2me energy, that is represented by phi here. Okay. Now, if the two conductors, that is the tip and the sample, are very close, then what happens? The leak out electron wave functions overlap, and then a small voltage V applied between the tip and the surface causes tunneling to take place. Now, if a small potential is applied between the tip and the surface, then tunneling will take place. That is, a tunneling current I flows across the vacuum gap. Now, if the two conductors, that is the tip and the sample, are very close, then what will happen? Their leak out electron wave functions will overlap, And when a very small bias is given, that is a very small voltage is applied between the tip and the sample, then the electrons will readily tunnel from the tip to the sample or from the sample to the tip, depending on the polarity of the bias. That is, a tunneling current flows across the vacuum gap. Now, at low voltage and temperature, this tunneling current I is proportional to e raised to minus 2kd, where d is the separation between the tip and the substrate, and k is equal to root of 2m phi by h cross, which we discussed earlier. So, the tunneling current I is dependent on one factor is the separation between the tip and the surface, and the other factor is phi, that is the potential barrier height, because 2 is a constant, m is a constant, h cross is another constant. So, the tunneling current depends on two factors. One is the separation between the tip and the surface, which is d, and the barrier height h. Next, we have to learn what is called the local density of states. Now, what is meant by density of states? It represents the amount of electrons that exist at specific values of energy. Now, by measuring the tunneling current in an STM, we can calculate the local density of states. That is because density of states, once again I'll tell you, it represents the amount of electrons that exist at a specific value of energy. So, specified or specific values of energy, and tunneling conductance sigma. Conductance, resistance is V by I, conductance is its inverse, that is tunneling conductance sigma equal to I by V is proportional to the local density of state. So, by measuring the tunneling conductance, we can find out the density of states. Now, keeping the gap distance a constant, the change in current with respect to the bias voltage can be measured. That is, in this relation, the conductance can be found out, that is I, which is the tunneling current, with respect to the bias voltage can be found out, and by measuring these two, the local density of states can be calculated. Moreover, by changing the polarity of the bias given, the local occupied and unoccupied states can be found. Okay, so by changing the polarity of the bias, that is either the tip is given a negative bias or this tip is given a positive bias. The tip and the sample, or tip and substrate, are given positive and negative bias respectively. In the first case, we give the tip a negative bias. Then in the second case, we can give the tip a positive bias. Now, depending on the polarity changed, depending on the way in which the polarity is changed, the occupied and unoccupied density of states can be found. That is, if the tip is negatively biased, then the electrons can flow from the occupied states of the tip to the unoccupied states of the sample. That is, we are understanding that there are unoccupied states in the sample when you get a current flow there. If the tip is positively biased and the electrons tunnel from the occupied, then the electrons tunnel from the occupied states of the sample to the unoccupied states of the tip if there is a current flow in that direction. Thus, by changing the polarity, the local occupied and unoccupied density of states can be found. Next, a few STM applications. STM is used for the one that we learned, that is surface studies, to study the metal and semiconductor surface topology. That is for the surface study of semiconductors like silicon, which are used for microelectronics device fabrication. Then it is used in metrological applications. That is, the micro and nano topography of a surface is needed in applications like making high precision optical components, disk drive surface roughness, etc. So, it is used for, in such cases, that is, the STM phenomenon is, or STM, the equipment is used for during the synthesis of high precision optical components and for measuring the disk drive surface roughness. In these cases, the STM is used in combination with SEM, that is the scanning electron microscope. Okay, so those are the metrological uh, applications. That is, metrology, the term means the science of weights, or the weights and measures, or it's a science of measurements. Okay, so for the making of high precision optical components and in the development of the disk drive surfaces, which are all involved in these metrological fields, or involved in metrological applications, we use this equipment, that is the scanning tunneling microscope. It is used for the surface studies in combination with the SEM. The third application is the manipulation of atoms. That is, suppose there is an atom which is physisopt to a surface. That is, there is an atom which is physisopt, means it is, there is a surface here and there is an atom here. Now, by using the probe tip, what we can do is we can move this atom from one position to the other by moving with together with this probe. That is, the tip is placed directly over the physisorbed atom and it is lowered to increase the attractive force between the atom and the tip, and by increasing their increasing force, by increasing the tunneling current, and the atom is then dragged to the desired position by the tip. നമുക്ക് വേണ്ട സ്ഥാനത്തേക്ക് ഈ ആറ്റത്തിനെ നമുക്ക് ഈ ടിപ്പ് ഉപയോഗിച്ചുകൊണ്ട് നീക്കിക്കൊണ്ടുപോകാം. So, that is the manipulation of atoms. That is, an atom physisorbed to a surface is moved across the surface using the tip of the STM. The tip is placed directly over this physisorbed atom and lowered to increase the attractive force by increasing the tunneling current, and the atom is then dragged to the desired position by the tip. So these are some of the applications of the STM. It is used in the surface morphological studies that we already know. It is used for studying how the surface topology is of the synthesized nanomaterials. Then it is used in metrological applications. That is, it is used in the making of or synthesis of high precision optical components and disk drive surfaces. It's used in the manipulation of atoms. That is, it is used to drag atoms from one position on the surface to other position by bringing the tip very close to these atoms and increasing the tunneling current. The atom gets dragged with the help of this tip to another point on the surface of the sample. Okay, so I hope this session where we learned about the quantum mechanical tunneling mechanism in STM and some basic applications of STM is clear to all of you. If you have any doubts, please do contact. Thank you.